I'm Jessica Lundquist in the Department of Civil and Environmental Engineering.
And what do you study?
Snow. So if you look at a lot of the work that's been done by the Climate Impact Group here, Phil Mote and Alan Hamlet's work, you'll see that of all the Washington West Slope Cascades are some of the most vulnerable to climate change. So why is that the case? Why are we more vulnerable than Colorado? And the reason is because most of our snow is in what we call the intermittent snow zone. That basically means that it snows, it melts, it snows, it melts. That the only reason we have snow in a lot of the places up here is because it snows so much. Colorado, it doesn't snow nearly as much. If you're putting temperature sensors in trees, you can reach them. You don't have to throw them up in the tree. Here, we have a ton of water. And so that water is actually melting throughout the winter. It doesn't just wait until the spring. The big issue for are we flooding is how much area is it raining over. Basically, how much area it's raining over depends on how far up the mountain. Basically, watershed is the entire area over which water collects and spills to your river that you built your house next to. And so if we basically have a very, very high rain snow line, then it's raining over the entire watershed. Raining hard over the entire watershed, amount of water in the river, just precip times area, is going to be larger by a factor of 2, 3, 4. That's one of the concerns with the Howard Hansen Dam right now, and why there's been the media blitz about, basically they've got vertically pointing radars, which look straight up in the sky and can tell where a snowflake melts and turns into a droplet. That gives you the elevation where snow is changing to rain as it falls through the atmosphere. And that lets you know how much area will be contributing to potential flooding in the river. So what we found is that in the state of Washington, where they put the long-term high elevation temperature stations are mainly at the passes, mountain passes, where the road goes across, right? Makes sense. That's where you can maintain it. That's where you can put a whole bunch of heavy stuff and make sure it's working all the time. So consider Snoqualmie Pass, where the ski resort is, up by Alpental. And basically what happens here in the winter is on the east side of the Cascades, you get trapped a whole bunch of very, very cold continental air. On the west side, we have more warm maritime air, right? It's more mild in Seattle than it is in Spokane, right? And so if you're at the pass, you essentially have that cold air from the east side creeping through. That makes the pass colder for its elevation than anywhere else in the mountain range. Now, what you then assume is you have lots of measurements down in your valley, where we live in Seattle, and then we have this really cold measurement. So we assume that temperature decreases a whole lot with elevation. We fit a line to our measurements and we say, okay, we've now, temperature decreases with elevation, and we'll then map what temperature is all over the mountain range. That tells you where it's rain and where it's snow, because you know what the temperature is, where it's freezing, where it's not. You put out a whole bunch of these and you suddenly find out that that one station is not really representative of what's happening most other places. That if you're on the west slope and not where that cold eastern air can get through, you're a fair bit warmer at the same elevation. That means that temperature isn't decreasing as much with elevation, and that if you were going to fit a line to describe temperature everywhere in the mountains according to elevation, you would want a different line than what you might assume from one measurement. So essentially, you can start capturing spatial variability. You can take 100 measurements and say, okay, this is what's actually happening